Hello everyone, I'm Norman Wahlberger. We're here at the University of New South Wales, and today in this course on differential geometry we're going to have a look at metrical structure in a rather general way, and then we'll get to curvature of a parabola, start talking about curvature in a somewhat non-standard way. Okay, so when we talk about metrical structure in geometry, it's useful to separate in our minds these two cases of affine versus projective geometries. Both of them can be imbued with metrical structure. So the metrical structure is something that you add to both of them, and it's usually done in a parallel form for both of them. It's usually via a symmetric matrix. And this provides us with a rather general approach to metrical structure that's going to be important for us because we're actually interested in applications of differential geometry to physics, to especially physics of special and general relativity. And although we may not get very close to understanding that, we're still aiming in that direction. So what we want to do is we want to be a little bit more flexible about metrical structure than usual. So usually when we talk about metrical structure, we're talking about Euclidean geometry. Today we want to enlarge our view a little bit. Okay, so let's start with the affine situation, which is by far the most familiar. And we'll start, say, in the plane, the affine plane, just with coordinates x and y. So a vector is a typical vector, say x and y, like this. And a metrical structure is given by what's usually called an inner product or a dot product, and it's given as follows. So if A is a symmetric matrix, 2 by 2 symmetric matrix, then, and let's fix it, then we can define V, say 1 dot V2 to be V1 times A times V2 transpose. Okay, by which we mean, say, x1, y1, and then the matrix A, and then the x2, y2 on the right as a column. Specifically, that's A, x1, x2, plus B times x1, y2, plus B times x2, y1, plus C, y1, y2. In this case. All right, so that's an example of a symmetric bilinear form. And what does that mean? Well, it means, first of all, that V1 dot V2 is the same as V2 dot V1. That's the symmetric condition. And then the bilinear condition is that if we have some combination, say A, V plus B, W dot U, let's say, then that's the same as A times V dot U plus B times W dot U. And there's a corresponding bilinearity with respect to the second variable that follows from the symmetry of it. Associated to this bilinear form is a quadratic form. Okay, where we're letting V1 and V2 be equal. So we'll write that as Q simply of a single vector V, and that's by definition V dot V. Or in terms of our matrix, V times A times V transpose. And we're going to give this number a name, so we're going to call this the quadrants of the vector V, which is a reasonable name. Also associated to this is a notion of perpendicularity. Notion of perpendicularity is that V is perpendicular to W. We define that to be precisely when the dot product is 0. And another notion is the notion of a null vector. A null vector is a vector which is perpendicular to itself. So that's a vector V, such its quadrants of V, or V dot V, equals 0. Okay, so these are general things that apply not just to the Euclidean situation, but to a general quadratic form or general bilinear form. Given any matrix A, we can associate this symmetric bilinear form. We can associate to it also the quadratic form. We have a notion of perpendicularity. We have a notion of null vector. There's also a sort of a geometrical object that's natural to define. So we can talk about something like a circle. That's also a metrical structure. So a circle is defined by an equation. Now suppose we have some variable vector x and some fixed point c. Doesn't have to be the origin, can be wherever we want, and some fixed number, okay. Then the equation quadrants of the vector x minus c equals k. That defines a circle. All right, so this is a generalization of things that you're familiar with in the Euclidean setting, but we want to incorporate a wider story, particularly one that's geared towards relativistic geometry. So let's have a look at some examples now. So the main example, the most familiar one by far, is what you get when you let A be the identity matrix. In that case, the dot product is just the familiar x1, x2 plus y1, y2. In that case, the perpendicularity is just the usual notion of perpendicularity. And circles are the usual kinds of circles. So a circle looks like x minus a squared plus y minus b squared equals k. The quadratic form is just x squared plus y squared. And here throughout I'm sort of adopting the convention that v is the vector xy, v1 is the vector x1, y1, v2 is the vector x2, y2, and so on. All right, that's very familiar. But now let's have a look at a relativistic example. Let's look at what happens when we look at the matrix 1, 0, 0, minus 1. In this case, the symmetric bilinear form looks like x1, x2 minus y1, y2. And the quadratic form is x squared minus y squared. And what does perpendicularity look like? Well, first of all, we have to draw these special lines. The lines x equals y and x equals minus y. These are the lines of null vectors. So now any vector on these lines are null. For example, if you have a vector 1, 1, then its quadrants will be 1 minus 1, which is 0. And what does perpendicularity look like in this case? I should make this a little bit more like a slope one line. So here's what perpendicularity looks like. If you have some vector, let's say Lm, for sake of argument, then what would be a perpendicular vector? Well, we'd have to find another vector so that the dot product would be 0. Over here, what we would do is, if this was vector Lm, then to get a perpendicular vector, what we could do is we could choose minus ml. All right? That's a perpendicular vector in the Euclidean case, because the dot product is 0. Over here, what we should do is we should choose the vector ml, because now the dot product will be m times l minus l times m, which is 0. So the perpendicularity, here it is right here, it's quite different than it is in the Euclidean geometry. These two vectors are essentially reflections of each other in this line y equals x. Or if you took its negative, you could also look at this one here. The negative would be the reflection in the line x equals minus y, so it's really the same story. So that's perpendicularity, has quite a different nature. So the closer a vector gets to this null line, the closer its perpendicular is to itself. And when it actually gets on to be on the null line, then its perpendicular vector is itself, which is just another reflection of the fact that these are the null lines. They're the vectors who are perpendicular to themselves. That's what we mean by the quadrants, which is v dot v is 0. In the Euclidean case, there's only one vector which is perpendicular to itself, which is the 0 vector. Here, in the relativistic setting, it's a richer geometry in some ways. We have this whole pair of lines which are all null vectors, which we don't have any analog for that in the Euclidean geometry. And what about circles? Well, a circle is defined by an equation of the form quadrants between a vector and some other point will be some fixed value. So it'll be x minus a squared minus y minus b squared equals k. That's what circles look like in this case. So maybe we should say circles sort of in quotes, because they don't actually look like circles to us. They look, of course, like hyperbolas. And we can draw them. So for example, if there happens to be one, then there would be the circle defined by quadrants of v equals 1, where x squared minus y squared equals 1. Or we could look, say, at this hyperbola. That would be quadrants of v equals minus 1. So we have three different kinds of circles. We have the null circle, if you like, quadrants of v equals 0, which is this pair of lines. Quadrants of v equals 1 is this kind of hyperbola. Quadrants of v equals minus 1 is this kind of hyperbola. And I'll mention a closely related one, which is just really a variant of this one, but physicists find it useful to change coordinates. So there's another example where we take the matrix A to be 0, 1, 1, 0. In that case, the dot product will look like this. v1 dot v2 will be x1 y2 plus x2 y1, if you make the computation. And the quadratic form looks just like 2xy. What's the picture in that case? Well, in that case, the null lines are these ones here. So this is quadrants of V equals 0. The circles, say quadrants of V equals 1. So hyperbola, 2xy equals 1. While if we set it equal to minus 1, it would be like this. So quadrants of V equals minus 1. And of course, if we could scale up, we would get quadrants of V equals, other numbers. It doesn't have to be 1. We can scale up and down. So that's what the circles in this geometry look like. They're both rectangular hyperbolas, both in this situation and this situation. Now, for future reference, these three particular geometries are quite interesting. So we're going to give them some names. So these two here are, of course, relativistic geometries. And they're these days may be associated with the name of Einstein and maybe Minkowski, but they were also studied before that by the physicist Lorentz. So often they're called Lorentz spaces. And we're going to give them some names. In fact, I'm going to call this geometry, the familiar one that we all know and love, the Euclidean geometry, I'm going to call that blue. And I'm going to call this one red, and this one green. All right, so when I refer to blue geometry, I'm talking about the ordinary Euclidean planar geometry. I'm talking about red geometry, I'm talking about this relativistic geometry, and green geometry, this version of it. These two are almost the same, right? They're just sort of rotated from our point of view. But nevertheless, it's useful to keep them separate. All right, so more briefly, let me just mention that we can also do this in 3 dimensions. And so the basic story is really the same in 3 dimensions. The crucial starting point is a 3 by 3 matrix, and I like to write it like this: F and G. So that's a symmetric 3 by 3 matrix. And maybe I didn't say before, but usually, not always, but usually we like this matrix to be invertible. So usually we take the determinant to be non-zero. Okay. And then we just proceed exactly as above. We define an inner product on vectors. V dot W is VA W transpose. We define the associated quadratic form. And we define circles as quadrants of between V and C equals K. We define perpendicularity by the bilinear form being 0. And we also define null points, or null vectors. Are those vectors V where quadrants of V equals 0. So algebraically, it's exactly the same, but geometrically, the story is somewhat richer. So the first example is just when you have the ordinary identity matrix, and there we get the usual inner product. In 3-dimensional space. And let's talk about this other one, this more relativistic one, where we have 1, 1, and minus 1, and 0 is elsewhere. So now the quadratic form, if V is x, y, and z, then V1 dot V2 is x1, x2 plus y1, y2 minus z1, z2. And the quadratic form is x squared plus y squared minus z squared. All right, sort of in keeping with our former usage, let me label the axes with capital letters now. We're in three-dimensional space. So the primary object of interest is the null vectors, and maybe I will write them in blue. So these are the vectors such that x squared plus y squared minus z squared equals 0. Physicists would call that the null cone. And it's associated with the motion of photons, things going at the speed of light. For a physicist, these are spatial dimensions, and z is the time dimension. And so this particular speed sort of corresponds to a particular sort of maximum speed, the speed of light, in any one of a circle of directions. In this case, the plane represents the space, so it's not really space, it's more a plane. But we don't need to understand any of the physics, it's just a purely mathematical construct. So after we have the cone, we can talk about a perpendicularity. The perpendicularity is a lot like the red perpendicularity. Okay, so if you have a vector, let's say LMN, then the corresponding perpendicular plane, well, it will sort of have to reflect that vector in this thing here, and you actually get a plane. So in the plane of the board, if this is on the board, you would reflect it, and then you would let them come out perpendicularly. So this plane would have equation Lx plus my, not plus nz, but rather minus nz equals 0, because that's the nature of the quadratic form. The circles now are spheres, and they're of two different kinds. So here would be quadrants of V equals, say, 1. That corresponds to the equation x squared plus y squared minus z squared equals 1. That's a hyperboloid of revolution, or sometimes called a hyperboloid of one sheet. It's what you get when you rotate this hyperbola around the z-axis. Hyperboloid of one sheet. And the other case, when we go up here, if we take this hyperbola in the plane and rotate it also around the same z-axis, we get a different kind of hyperboloid. We get one that consists of two separate kind of hyperbolic cups. And that's then quadrants of V equals minus 1. And that's usually called a hyperboloid of two sheets, because there's actually two separate parts to it. Two-sheeted hyperboloid. Okay, so let's relate this now to the projective version. So how does the projective story sit inside here? Remember that in the projective plane, what we're doing is we're considering lines through the origin. And we're viewing those lines through the origin by looking at the viewing plane z equals 1, which is usually right here. So if we're looking at this entire story sort of projectively, from the point of view of this plane z equals 1, then the first thing that we see is this null cone. The null cone intersects our plane in a single circle, which will be the unit circle in that xy plane. So now in the x, little x, a little y plane, this will be the circle x squared plus y squared equals 1. It's what you get when you said capital Z equals to 1. And the perpendicularity that was happening in the big three-dimensional space gets represented here by the polarity with respect to this conic. Okay, so the three-dimensional perpendicularity is really the same from this projective point of view with the polarity with respect to this unit circle x squared plus y squared equals 1. So what do I mean there? Well, I mean if we took our, say, vector that we were looking at through L and M and N, then that will meet this viewing plane in some point. And if we look at its perpendicular plane, the plane that I drew here, and see where it meets the same viewing plane, then the relationship between this point and this line in the viewing plane is exactly the polarity of Apollonius. Namely, if you draw tangents, you get to those 2 points where the perpendicular plane meets the unit circle. All right, so there's a theorem that I want to show you that I mentioned last time, sort of to complete the discussion here about tangents. And it's a very nice theorem that allows us to think about perpendicularity in a general affine geometry in terms of tangents to circles or perhaps spheres if we're in higher dimensions. So the theorem is that if V dot W is a symmetric bilinear form in, say, 2 dimensions or maybe 3 dimensions, then perpendicularity, V perpendicular to W, which is the same as V dot W equals 0, this is really geometrically the same as that V is tangent to the circle or sphere quadrants of x equals k, which is the quadrants of W. Let me illustrate it in the case of the red geometry. So if we have, here's our plane, we're talking about the red geometry. If we have some vector W, and we look at the circle determined by its quadrants. So these are all, this is the equation quadrants of x is the same as the quadrants of W. All the things which have the same quadrants as W. Then at that point right here, we can draw a tangent plane, or in this case a tangent line. And what we're saying is that any vector which lies in this tangent line, say V, is characterized by this perpendicular property. So you can think about perpendicularity as being perpendicular to circles. I remind you that in Euclidean geometry, if you have an ordinary circle and you have a radius, then the tangent at that radius is perpendicular to the radius. Right? That's another way of describing what perpendicularity is. What we're saying is that exactly the same story here, but for a general symmetric bilinear form. All right, and the proof is not too hard. The proof just requires us to be clear about what does a tangent mean. So a tangent means it's a line that meets the conic once. Not 0 times, not 2 times, but exactly once. Okay, so let's have a look at what does this condition mean. Suppose we look at V plus, we'll start with W. So we'll look at W and we'll look at the line W plus TV. That's this line here, typical point W plus TV. We'll ask, when is this a tangent? When is this a tangent line to the conic quadrants of X equals quadrants of W? All right, so what is the condition? What is this the equation of this conic? The equation of this conic is X transpose equals W transpose. That's the equation of the conic, and we're asking, when does this thing lie on this conic? So W plus TV lies on it precisely when W plus TV times A times W plus TV transpose equals W transpose. Okay, but this isn't bilinear, so we can rewrite this as W transpose plus 2 times V transpose plus T squared V transpose equals W transpose. And I've used the fact that it's symmetric so that WAV is the same as VAW transpose. There's 2 terms that add up to this one. All right, now fortunately this one here and this one here cancel. And there's a T. Yes, there's a T, of course. A very important T. So after we cancel these common terms, we get T times 2WAV transpose plus TVAV transpose equals 0. And we're asking, when does this have only one solution? For which V's does this have exactly one solution? Well, one solution is T equals 0. That's always going to exist. That corresponds to the point that W that's actually on the conic. Are there going to be any other solutions? Well, so if we solve this for T, then we would get T equals this over minus this. And that's going to be 0 precisely when this is 0. So if we want there to be only one solution, we have to make sure that this term is 0. So this has one solution, exactly one solution, precisely when WAV transpose equals 0, i.e. when we're saying that W is perpendicular to V. Okay, so now I'd like to go back to a very simple thing initially. We want to have a parabolic view, let's say the parabola, and its curvature. Okay, we're going to be adopting a somewhat non-standard view of curvature, and it's going to be all based on parabolas. Okay, the standard view is that circles are the essence of curvature, but our point of view is going to be that we're going to shift towards parabolas instead, and that will allow us to generalize curvature in a better way to higher dimensions. allow us to generalize things to better higher dimensions. So we're going to start with a very simple case, just a sort of a first study, and look at a very simple curve, perhaps the simplest one besides the line, general parabola. Y equals ax squared going through the origin. And what we're interested in, the question is, how curved is this thing at the origin? What does that mean? Yeah, that's the question. How curved is this thing at the origin? It's somewhat curved, but how do you say what it is? Well, the first thing that we're going to do is we're going to find the focus of this thing from going back to the classical definition of a parabola. So suppose that we have some focus, and we'll put it here by symmetry, so at the point 0, f. And I remind you that the classical definition of a parabola is that it's what you get when you take the locus of a point, which is equidistant, or equiquadrants, from focus to a line. Okay? Focus and directrix. All right, so what the condition is that the quadrants from x to f should equal the quadrants from x to this line, let's L. It's a classical definition of a parabola. All right, if x is our point, say x, y, we want this to be y equals minus f if we want 0 to be sort of equidistant between this point and this line. Right, so we can write down an equation and figure out what f must be. So this quadrants between x and f, that's going to be x squared plus y minus f squared. And the quadrants between x and the line, well, it just depends on the y coordinate here, so it'll be y plus f squared. Okay, so we expand this out and we get x squared equals, the y squareds cancel, the f squareds cancel. There's a 2yf here with a minus sign and 2yf there, giving us 4yf. Or maybe I should write 4fy. And if we compare that, write in the form y equals 1 over 4f times x squared, then we see that the relationship is that a equals 1 over 4f. So if we know what a is, we know what the focus is pretty quickly. Okay, so now let's do something else. Let's have a look at a normal. So if we look at a tangent line here, then let's write this point now as t and a t squared, because it's lying on the parabola. Then a direction vector for this will be 1, 2, a, well, right as a vector. 1, 2, a, t is a direction vector. And that means that the normal at this point here will be a line which has the equation 1 times x plus 2at times y. And then it's got to go through the point tat squared. So if I plug in tat squared, I get t plus 2at cubed. At squared, there should be a square here. Thank you. Okay, and if I want to look at this place where the normal meets the y-axis, well, I have to set x equal to 0, and I get y equals t plus 2a squared t cubed over 2at, which is the same as 1 over 2a plus a t squared, I suppose. And then if I look what happens as t approaches 0, as t approaches 0, this point here, which I've just calculated, will approach 1 over 2a. So as t goes to 0, this approaches the point 0, 1 over 2a. And that's the center of curvature. In the 17th century point of view of place where normals, adjacent normals sort of meet, once we have a normal pretty close to 0, they're all going to meet at this point here. And that point now has coordinates 0 and 1 over 2a. I remind you that 0f was actually, this focus was 0 when we said f was 1 over 4a. So we have established the theorem that at the point 0, 0, the parabola y equals ax squared has, well, let's list what we said. We said the focus at 0, 1 over 4a. Center of curvature, zero over 1 over 2a. And then it's usual to define the radius of curvature to be just the displacement between the vertex and the center of curvature. So there's a circle centered here. It's a circle of curvature, and its radius will just be this quantity here, which is 1 over 2a, because that's the coordinate. So the radius of curvature, which we could call r, is 1 over 2a. And the actual curvature, which is by definition 1 over, well, usually called k, it's little k. It's by definition 1 over r, 1 over the radius of curvature. That's going to be 2a. Okay, so that's the parabola, classical parabola with parameter a. We have computed various things about it. That's all good, but what we would really like to do is to extend this and not understand just this parabola, but understand a more general parabola. So next time we're going to look at more general parabolas and more general formulas for curvature. And we'll see that we may have to be a little bit more flexible in our thinking. See you there.